morning. So, I was talking about optical non-linearity. Let me now start it all over again little bit. Optical non-linearity. Optical nonlinearity is a field which is of tremendous technological importance. So, engineering as well as physics as well as chemists, they all it will be useful for them, the optical non-linearity, and the subject called photonics. Photonics uses optical non-linearity. So, before we do that, I will first tell some rudimentary ideas what is optical non-linearity, and then we chemists, we cannot, this is such a vast area, I cannot describe you. Also my knowledge is not that great in those areas. Okay. So, those are domains of electrical engineers and physicists, instrumentalists like that, and but they cannot do anything unless we make compounds. So, we are the main people to make optically nonlinear active compounds. So, before I do optical nonlinear active compounds, okay, I will tell you what is optical nonlinearity in a very nutshell. Okay. So, now some materials, some compounds, if I hit it with a photon, then the polarizability is proportional to E. So, photon comes from electromagnetic radiation, it has electrical and magnetic component. So, this electrical component E will induce a polarization in your compound. What is polarization? I will very simple example I will tell you that if you take a iron ball and a rubber ball, what happens? Iron ball I cannot deform, but a rubber ball I can squeeze it and deform it. From a sphere it can become a deformed structure and all that. So, I will say rubber ball is more polarizable, okay, compared to an iron ball. So, that is polarizability. Polarizability means in chemical sense that in a chemical compound, if the electron density, okay, from its equilibrium, that compound we have thermodynamic equilibrium. Now, if I hit it with an electromagnetic radiation, then what will happen? It will become polarizable, but not with this ordinary light. I have to use laser light. Okay. So, some chemical compounds where polarizability linearly varies with the electrical component. So, I say P is proportional to E, or I can say P equals alpha E. In language I will say that polarizability for most molecules are linearly varies as the electric vector. Okay. P is proportional to E, that is what it means. Okay. And this is the coefficient. Okay. So, now if I some materials whose electron density can be deformed, number one, and in those molecules I will come in a minute what molecules, what should be their structures, those are our concern, right, chemist, we have to build. So, now those molecules, suppose we know how to build. So, if on those molecules I hit it with laser light, then the polarization is no longer linear, but polarization or say molecular polarizability. Okay. Molecular polarizability non-linearly varies. What does that mean? That means alpha E plus beta E square plus gamma E cube plus dot dot dot. It goes on. That means, here polarizability non-linearly varies with E. E is the electric vector. Okay. This is first hyperpolarizability beta, first hyperpolarizability, and gamma is second hyperpolarizability, and so on. Or we can say that beta is the second order non-linear optical second linear effect, second order optical non-linearity, gamma is third order optical non-linearity effect. Okay. So, we can say that, and P is molecular polarizability. We are discussing molecule. Okay. All right. So, now here I first talk about second order optical non-linearity. Now, I am talking about second order optical non-linearity. Second order optical non-linearity. So, beta is the, what is beta? Beta is the quadratic or first hyperpolarizability beta, I told you that, and this is the second order non-linear optical activity comes from this beta E square. Okay. Now, the question is, which molecules are expected to give high beta values? That is my aim. As a chemist, we know that these things are very important in photonics, and there are so many things can be done. Now, what is but I have to know little bit of those things, unless then only I can design my compound. Okay. So, what happens? The compounds that are expected to give high beta values is first molecular hyperpolarizability. This is linear hyperpolarizability. Okay. This is first non-linear hyperpolarizability, second non-linear hyperpolarizability. Okay. So, in the second order optical non-linearity, the molecule should be like this. There should be a donor, let me write as D, and then acceptor molecule and donor molecule. What donor acceptor? Electron donor, electron acceptor, and now there will be a pi bridge. I write like this, maybe little bit yeah. Okay. So, this is pi bridge. When molecule one side is donor, one side is acceptor, and this is pi bridge. These kind of molecules are expected to give high beta values. Okay. Molecules, I am talking about molecules. So, therefore, when I am trying to synthesize, I am a chemist. So, I decided to work on optical nonlinearity. So, I have to synthesize some new molecules which will give high beta values. Okay. So, what I will do? I look at these things and I look at which molecules are expected to give high beta values. These are if you look at carefully all molecules, then these are the important points to be made, to be understood and to be memorized. for getting molecules with high beta values. What is that? Excited state, I am writing these things. Excited states, electronically excited states, close in energy, close in energy to the ground state. To the ground state. That is one property. Number two, why it is so? Because if the excited state and ground state are closer in energy, then this energy should come in the infrared or visible light. That means, I can take infrared laser or visible laser, which are easily available to make my, to get electrons excited, okay, or deformed. Okay. So, that is why we need close in energy. Number two is large oscillator strength. Large oscillator strength for the transition. That means, large oscillator strength for the transition means, if I hit the compound with a laser, then it will absorb very easily large amount of energy and go to the excited state. If it has a low or small oscillator strength, its absorption will not be many. Suppose I will tell a number, maybe 10 molecules will go up for a low oscillator strength molecule, okay, for the transition. Now, if the transition is large, then what will happen? Maybe thousands of molecules will go up. Don't count my word of 10 and 1000, I just meaning it that with large oscillator strength, more and more molecule will go to the excited state, or to the excited state means when it goes to the excited state, it will be more deformed. It will be more deformed, that is, it is liable to be deformed more. Okay. So, polarizability will be more. And number three is very important, a large difference between the ground state, between the ground and the excited state dipole moments. What is the meaning of this? Excited state dipole moment, if it is large, that means charge separation is large. Okay. Then what will happen? If charge separation is large, so there is a charge, positive and negative charge. So, electrical component of the electromagnetic radiation will interact much stronger, because my dipole moments are larger. If the dipole moment is low, that means electrical component will not be able to interact very strongly. Okay. Charge interacts with charge, electrical component will interact with electrical. So, electrical means charge separated charge. So, that is why if the dipole moment in the ground and the excited state are different, then it will interact very strongly. So, that is the criteria. These three are very important point to understand before you embark on synthesizing this molecule. Before I do, there is another important thing. These I am talking about molecular, okay, at the molecular level. But when I am trying to go to say some uses, okay, some practical uses, I cannot work with one single molecule sometimes, but I will work with say powder, little bit powder or some solid. Okay. In that case, of course, you will know that optical activity works both in the solid state, in the liquid state as well as in the gaseous state. This is important, okay, to know that they work in solid state, liquid state or gaseous state. Okay, where are we? So, we were talking about that these things are molecular. So, I am talking about molecular second order optical nonlinearity, molecular third order second optical nonlinearity effect and all that, and molecule must have these criteria 1, 2, 3 to give high molecular polarizability. Okay. So, molecular, but for uses, for practical uses I need bulk. So, bulk is also related like this. This is quite illuminating, quite important. Bulk. So, bulk polarizability P is also expressed in P, little bigger P you say, you can say. So, it is chi. I had for molecular that coefficient was alpha, alpha, beta, gamma, delta like that. So, now it is chi 1 E plus chi 2 E square plus chi 3 E cube plus, okay, all right. So, now the question is, a common sense will tell us high beta value means, so my I am now interested in beta versus chi 2. So, beta is the molecular and chi 2 is the is the bulk. Okay. So, because they are all same, so in a first hand we will say that high beta value means we have to make beta values high, because we want chi 2 to be high, and we will assume that beta value more means chi 2 is also more. That is right, but not always right. A beta value large does not guarantee chi 2 to be large. Why? Beta values will be large. Okay. Beta values are large for certain molecule, like say d pi a. Okay. So, d pi a, d pi a, that is what I have written. So, d pi a. So, if this is positive, it becomes delta positive and become delta negative. It makes a dipole, okay. It becomes a dipole and large dipole, so dipole. But when we have dipole, when we in molecular is all right, dipole, but when you take about some solid macroscopic amount, then what happen? Say dipole I express is this way, positive side, negative side. So, when I have dipole, when I get the solid, not one molecule but lots of molecules solidified, then they solidify, like if one is this way, the other one will be this way, because they are charged. These are positive, negative. So, negative, positive. Okay. So, two dipoles will not be parallel, but anti-parallel crystallization. So, they will be anti-parallel. So, if there is a strong dipole for the molecule, then most of the cases it will become anti-parallel crystallization, anti-parallel. If it is anti-parallel, then we can calculate and find that, and calculation will show that chi 2 is equal to 0. So, here is a contradiction. We want beta value to be high, large, okay. But in certain cases, if it forms a dipolar, if it is a dipolar beta values, then what will happen? It will be anti-parallel, and if it is anti-parallel, calculation will show that chi 2 becomes 0. So, no good. We are not interested with beta as much as we are interested in chi 2, because we want to use this for some purpose, and so for some purpose one molecule cannot be useful. We want some solid, okay. Some solid has large number of millions of molecules. So, if they are anti-parallel, that means my chi 2 will be 0, okay. Chi 2 will be 0. So, that is one important point. Second point is, so then what to do, okay, what should we do? If they are anti-parallel also, so in crystallography, you do not know crystallography, but just take my word for it, they will crystallize in this kind of molecules, will crystallize in centrosymmetric space group. Centrosymmetric, let me write little bit clearly, crystallize, I will take a new page. So, anti-parallel orientation, anti-parallel orientation of dipoles, that you understand now. We said that if it is a dipole is strong, it will be anti-parallel. This is plus, this is minus, this is plus, this is minus. So, it will be like this. So, anti-parallel orientation of dipoles, they will crystallize more often than not, crystallize in centrosymmetric space group. You probably did not understand anything I just wrote, but take my word for it. So, I will tell you very in a rudimentary fashion that a compound can crystallize in centrosymmetric and non-centrosymmetric. Okay. Centrosymmetric means they are symmetric, and non-centrosymmetric means they are not symmetric. But more than that, you do not know space group, you do not know all these things. Okay. So, I leave it at that. Parallel orientation parallel orientation. So, parallel orientation of dipoles. Dipoles parallel. Parallel means this is positive, this is negative, and I will say this is positive, this is negative. So, both are like this. Okay. If they parallel, then what will happen? They will be crystallized in non-centrosymmetric space group, because they are not symmetric. So, non-centrosymmetric space group. Space group. So, therefore, from this you can have an idea. Now, so what should be the compounds? For example, I will tell you this is a compound, a typical compound. I am telling you just Da something like that. Now, I am showing you this is used as a standard, okay, molecular polarizability. NO2. This is donor, NH2 is donor, NO2 is a acceptor, and this is a pi bridge. So, this is popularly called PNA. Okay. People using this optical nonlinearity studies. Okay. So, therefore, they used, all right. So, PNA is the standard. Now, the question is what I should be doing to make them parallel orientation, even though dipole is large. I can go from suppose a linear to higher order. Suppose I make a cryptand. So, now it will be only cartoon. Okay, only cartoon. What happens? So, here this is nitrogen donor, if I can put an acceptor. This is a donor, this is an acceptor, all right, so in all cases. Okay. So, these three component, if I look at it carefully, it is looking like this. Yeah. So, we look at 3. So, their crystallization in anti-parallel mode will be less probable. So, people have gone from this linear to this is called octupolar. This is known as octupolar molecule or a 3-dimensional say. So, 3-dimensional molecule, then it will have less probability of anti-parallel crystallization. Another thing is, another important fact I must tell you that if this is my dipole, okay, this is positive, this is negative say. Now, if in this situation I keep here an optically active center, a carbon, okay, optically active carbon here, that means my whole thing is now optically active. So, optically active molecules never crystallize in centrosymmetric space group. This is another important point. So, there are many important points I am discussing. Here I am saying that now I take a very large, or maybe I will write like this. This is one multi, but if you have to take linear D okay. Okay, and this maybe this is A, this is A, this is A. Now, if I put, I will put a single bond, double bond cannot have optically activity. Okay, so suppose this is my chiral center, chiral molecule. Okay, this is chirality. Okay, this is any group R1, R2, R2, and this is maybe starting with N something. So, then there will be chiral. If a molecule has chirality, you know that it cannot crystallize in centrosymmetric space group. A molecule with chirality has to crystallize in non-centrosymmetric space group. So, this is another technique. So, I will discuss this again next class. Thank you.